today we are going to do section 4.1. Now, before we start, I want to scan a bunch of stuff. Okay, first, I want to rescan the homework, the answers, I mean. We've already done this page, but I want to do it one more time. And being that we're in chapter 4, as you can see, we need to turn to the next page, which is awesome. Here is a further homework that goes all the way to chapter 6. I will show it to you here. Let's see, okay, and then perhaps a bit closer on top and a bit closer on the bottom. All right. I also want to show you some of the contents page that I forgot to do, I think, or maybe I didn't forget, I don't remember. But I want to show it to you. Sometimes it's helpful to see the contents page to when you're looking for stuff. Okay, do a quick search of where did I study this, that sort of thing. All right. Now here is contents page for the for our current chapter. Okay. Let's see. Yeah, I'll try to remember to show you the contents page for well, at each time that is. Let's see, it's not parallel. Yeah, something like that. Maybe a little closer. All right. I like to show you the contents page every time we start a new chapter. All right. So now let me show you the new chapter. Okay, chapter 4, page. Let me see how I'm going to hold this thing. Okay, 118 and 119, I believe. Let's keep this thing in the middle. Okay, that should be good enough. And a little bit closer on top. And a little bit closer on the bottom. All right. Next, page 120 and 121. Let's see. No, that's wrinkled. Why is it wrinkled? Let me fix that. It suddenly fixed itself. Maybe I was holding it wrong. Anyway, so let's get back to looking at this page. Here's page 120 and 121. A little closer on top. And a little closer on the bottom. Let's see. What am I doing? Okay, that should be good enough. Okay. Okay, so let's start section 4.1 on page 118. Now, please read. We're going to do the maxima and minima, which are rather similar to what we did in Calculus 1. There are a couple points that we will push beyond what we learned in Calculus 1. So please read the introductory part stuff yourself. Okay, and that is all the rest of these couple of paragraphs. And then we'll move directly to Theorem A on this page. Theorem A says that if you have a function that belongs to C1, now I want to emphasize again what the term C1 means. We've been looking at it in the past, so a couple of chapters at least. But you might have forgotten the exact definition, so I want to refresh your memory, and let's look at it right now. This is on page 8 of the book, okay? And it's by definition 3. Read this carefully. It says f of x is in Cn if fn of x, that is the nth derivative, is continuous, okay? In other words, remember that Cn, in this case C1 that we're talking about, isn't just a matter of, it's a the derivative exists to such as, for example, C1 exists. We're not just talking about that. We're talking about C1 doesn't just exist. It's even continuous. So that is what in general, what Cn means. So having said that, let's see what Theorem A says. It says if you have a simple function, right, one variable, nothing fancy, and then you have this, it has continuous derivatives, and then it has 3 points. There's A, B, and C, and then B is here, and C is somewhere inside A and B. And then there's a situation where f of A, so here's the function does something like that. F of A is, so let's say that's f of A is less than f of C up there, and f of B is also less than f of C. Now, if this situation is true, then there exists some number called x, okay, where f of x is going to be less than the f of big X. So we're going to find, well, let's say C is, I don't know, over here. We won't put it right on top. Let's say FC is over here a little bit. Okay, that's FC. And so if this is true, then we can find some number x, f of x here, okay, big X, that is, such that big X could be the same as C, or it might not be. It doesn't matter. But there exists some big X such that everything in this neighborhood, everything from A to B, f of the value of f is going to be less than or equal to the value of f at this big X. In other words, the maximum exists. Now, it's basically the function f of x is low at the sides and high in the middle. Okay, the middle referring to the big X. Now, we're going to skip the proof of this thing because it's similar to Rolle's theorem, and we don't want to restudy Rolle's theorem right now. So, and nevertheless, that, yeah, so please read the rest of this yourself, okay? And then, and I'm not going to cover it too much. Now, let's move on to example A, which is an application of this theorem A that we just did. Now, example A is in the using of theorem A is rather similar to what we did in calculus 1. Okay, so please do this part yourself, and then and I will show you what I did for example A here. Here is I used the function evaluation calculator because it expects you to take a bunch of derivatives, and so I used the derivative calculator over here, okay, to take all the derivatives, because I really rather not do that by hand. I mean, seriously, if you already know how to do something, you know, repeating it is not going to make you get any better, except wear you out. But of course, feel free to do it by hand too, and there's nothing wrong with that. And so so here's my function. I use the evaluation calculator, which automatically show me what the value of various things are. Okay, and then I use the derivative calculator that gave me the second derivative again, which I use the evaluation calculator that automatically gave me these values. I have the link of these calculators below this video, and probably I already mentioned it before too. But in any case, so here's the graph, and as you can see, the graph has two maximums and some kind of minimum at the origin, and then after that, it just take a dive on both ends. Which is, yeah, which you're familiar with that, but please do this yourself too, okay? So let's move on to what's next? Yeah, the next subsection 1.2, sufficient conditions. And let's look at theorem B. Now, theorem B is similar to what we learned in calculus 1, but it does take it a step further. That is, we're not just in calculus 1, we were talking about the second derivative being bigger than 0, and therefore is a convex up or down or something like that, right? This says, however, that it's not just the second derivative, but any kind of even ordered derivatives. Okay, if it has a specific quality, then it will give us a relative, what is this? Minimum, I believe. Yeah, so then in a very similar way, except now we're calculating stuff all the way, not just the second derivative, but maybe the fourth, sixth, whatever the even number is. So the condition, let's read the condition here. Condition 1 is f of x belongs to C2n. Okay, so it's continuous all the way up to 2n. And why is it 2n? It's just to make sure that it's even. And then f of k is of big X equal to 0. from 1 all the way to 2n minus 1. That is, no, yeah, so k start counting at 1, okay? And so, which means f of big X itself isn't necessarily 0, it's just, but its derivatives from 1 to all the way to 2n minus 1 is 0. And then condition 3 says f of 2n of big X is less than 0. Now this, of course, this theorem, we used less than 0 as an example here, but if it was bigger than 0, the theorem will work in a parallel or mirror way, okay? So, so if these three conditions exist, then there exists a positive number such that in the neighborhood of big X, we'll have the condition where f of X, everything else is going to be less than the f of big X. Did I say maximum or minimum? I mean maximum, because when the second derivative is, yeah, so everything is going to be less than it, which means, let me think before I say something wrong. Yeah, well, I don't know what I was thinking. Okay, the second derivative is less than 0. Oh, I don't know why I thought I said bigger. But in any case, if the second derivative is less than 0, you can imagine, for example, y equal to a very simple one, y equal to minus x squared, right? Then at x equal to 0, then the second derivative, of course, is going to be less than 0, and that's a local maximum. It's that simple. All right. So anyway, Anyway, so let's turn the page and see what it says. Let's look at the proof. That is, yeah. So it has, in that situation that we just talked about, it has a relative maximum, and yes, because it's upside down like this. So the second derivative in this example would be less than 0. Now to prove this, however, we're going to do something that we didn't do in Calculus 1. That is, we're going to pull out the Taylor expansion. Okay. Now here it is. I have written down here. The Taylor's expansion is on page 43 and 44, where this is the first part of the Taylor's expansion, and the second part is the Lagrange remainder of the Taylor expansion. That means psi there. Okay, and anyway, so once you write it out, then you remember the conditions. That is, the derivatives as at the point that we're thinking about, big X equals to 0 from the first to the 2n plus 1 derivative. So this term basically collapsed. Okay, there's nothing here, because we'll write the f of big X on this side. So f of x minus f of big X, that's the only thing that isn't 0 up to 2n minus 1. And the rest, this part disappeared. So we only have the remainder left, which plug it in, it looks like something like this, where psi is somewhere between small x and big X. It can be written this way or the other way around. Okay, and anyway, when I say the other way around, I mean big X can be here and small x can be here, because we don't know the order of their difference. Yeah. Anyway, so then if that is the case, then being that when you stare at this thing right here, okay, being that this thing is less than 0, we have decided that. Then as small x approach big X, then this thing we can find a value in this neighborhood psi such that, or should I say, f2n of psi will approach to some value delta that is going to be less than 0. And the reason for that is because f2n of big X is less than 0 as given to us by the condition. And also f2n, as you remember, is continuous. Okay, the derivative itself is continuous. So we're allowed to take its limit, and as it approaches stuff. So then So as a result, this sentence right here makes sense. That is, as small x approach big X, psi does also, and also f2n of psi approaches a negative number, which I call delta. And so as a result, then we got what we want. Is let me show you the book. So as a result, that being that 2n of at big X is less than 0, and the approaching is always going to be it approaches a value that's less than 0 as X approaches big X, then psi also approaches big X because psi is in between those two values. So as a result, if you stare at this formula that we just had, that means that this stuff here is being that it's an even power. Okay, this stuff here is always positive. This value is negative, which means fx minus f big X is always negative. So it's always less than 0. And that is what we are starting out to prove. All right. And well, the book then mentions a quick application of this in repeating example 1, which I already did when I showed you the example 1 a little earlier about calculating its second derivative. I guess I'll show it to you right now again. But please do this yourself. Okay, that's just that's very similar to what we do in calculus 1. So I won't go into details. See, I just typed in put the second derivative in there and find out that is what. Can you see that? Is yeah, negative, and then is local maxima or something, just like it says. So next, let's look at example B. Now, example B is similar to what we did in calculus 1, except that you're going to take a whole bunch of derivatives until something isn't 0 anymore, okay, which is what I did here. And notice that the graph looks like a plateau, which I thought that was kind of neat. And I've forgotten that these things look like that, okay? It gets rather flat and the higher power you go. So the f prime, we calculate all the derivatives up to the sixth one. Finally, that is not 0, and then that will give you something about f0 equal to 1 is the maximum. So please do that yourself as well. And so next, let's look at example C, a similar matter. Okay, except this time it has an odd power, and being that it has an odd power, then it has local. It has, what is this? What? Give me a second here. Okay, next, please do example C by yourself as well. I have done here, okay, in case you want to know how, what kind of work I want done. All I did is type this thing into the decimals calculator, and as you can see, that is, the evaluation calculator, which also plotted the graph, and as your book says, it has various minimum, relative minimums, maximum, I guess. Is there a minimum? I don't know. But anyway, figure that out yourself. It also says something about it has an absolute maximum and absolute minimum. And you might find like, what? Why would a function like this have an absolute maximum? The book is specifically referring to the limited domain of your x can only be from -2 to 2. Okay, that's the only reason that the absolute max and absolute min even exist. Now, this graph, as you can see, it might look pretty flat, you know, down there, like look how flat it is. But that's only because the graph is severely crushed. See, the x-axis goes from -20 to 50, which is 70 units width, whereas the x-axis only goes from -2 to 2, so there's only 4. To see this thing in a more proportional, in a square zoom, okay, that's what it really looked like. See, there's actually a slight bump there, but you can't see it in the big picture because the big picture is zoomed out too far. So your human eyes can't discern the difference there. But there's a small relative maximum right at that spot. Okay, yeah. So please do that yourself, and then we'll move on to the next thing. And so next, let's look at theorem C on page 120. We have, so this time we're talking about the inflection point. Now remember what that is. Okay, that's, and if you don't, I'll show you in a moment. Now the inflection point is best described as when the curve crosses its tangent. Okay, that is, it goes some way and then it decided to change direction. So it's been turning this way your wheel has been turning this way, you cross the inflection point, you start turning the other way. So the theorem is theorem C. The first f of x has to be continuous up to the odd power, okay, 2n plus 1, whereas the nth derivative start counting at 2. Start counting at the second derivative. That is, the first derivative doesn't need to be 0. Okay, we only care about the second derivative. So start counting as the second derivative, all the way up to 2n, missing the last one. It has to be 0, and then the n plus 1 point derivative is not 0. Now, if these three conditions apply, then f of x will have a point of inflection at big X. Now, the proof is identical to the previous proof in the previous theorem. What is that? Whatever, B or something. But we are going to use the exact same Taylor expansion that in theorem B, okay, which again writes like this. And then being that k, but remember k, f of k of big X start being 0 from k equal to 2 all the way to k equal to 2n, right? Yeah. So those are all 0, which means again everything in here gets knocked out with with the exception of f of x and f prime. F of big X and f prime of big X, like this, okay? So we have these two surviving terms, and everything else becomes 0 in the Taylor expansion, and here's the remainder. All right, now look at this carefully. You notice that the remainder, this thing is of course not 0, whereas this thing is raised to the odd power. Now before we had something that's raised to the even power, right, like this, which means this part is always positive no matter what x is in the neighborhood of big X. This is always, this part, just this part is always positive, not counting the small f. Whereas it's similar, but in a similar but not the opposite situation, that this part here is always, it will change from one side to the other as x approaches big X and pass it from one side to the other. It will either go from positive to negative or negative to positive, okay? And so because of the odd power situation, and as a result, this thing being not 0 means that the graph, what is that? That is actually the graph of f of x minus a constant, is point. My camera is forgetting how to focus. Okay, and so then is the graph, the difference between the graph and its tangent. In other words, it looks something like this. Okay, and so if you were to draw it out, this curvy line is f of small x minus f of big X. Remember, big X is just a point, so f of big X is a constant. So you move this thing to 0, and then f prime of x times x minus big X, that is the tangent at this point in question. At big X, that is. And so then you can see from this illustration that things went from one side, excuse me, all the way to the other side. So that's how this theorem will work in proving that the inflection point is exists. Yeah. So that's that. So please read this yourself as well, okay, to convince yourself what I just said. And with the next thing, let's look at example D, which I believe, example D, please also do this yourself. Oh, there's something at the top of the page that I want to mention to you. It says that it mentioned the corresponding ordinates. Now, you might not remember what this word means, like the word ordinate, and what that word means is the y coordinate. Okay, just want to quickly remind you in case you've forgotten the definition, and I haven't seen that in a while. Y coordinate is called the ordinate, whereas the x coordinate is called the abscissa. Okay, I don't use that word much ever, but it's there. So you should know what it is if you ever run into it. And so yeah, so example D is not much happening. You just take a bunch of derivatives and then finally figure out the odd derivative finally becomes non-zero. Okay, and what is that? I'm not sure. That doesn't seem done. Okay, let me check. Actually, it's done. Okay, because I have here x is to the power 0. If x is to the power 0, that's 1. So the fifth derivative is finally non-zero, and by the theorem we just looked at, that means there's an inflection point. So with that, we have come to the end of this section, and let's do homework. For homework, please do problems 1, 3, 7, 10, and 11. Okay, most of these problems feel like sort of a repeat of what we did in Calculus 1, so which is why I'm not asking you to do a whole lot of them. It's just a handful, and it doesn't hurt to do a little bit of homework to brush this stuff up. All right, so please do that, and then we'll talk about them. So let's talk about the homework problem 1 on page 121. The problem 1 is very standard, I think, similar to what we did in Calculus 1, so I won't go into detail here. I think I end up calculating an inflection point or something. Yeah, I guess. And then problem 3, similarly, there is a function. The only hard part of here is you have to remember how to take the derivative of x to the power x. And the trick is to turn it into the e log x to the power x, which becomes ex log x. Okay, remember log from this point on means natural log, period. Okay, so then we do whatever it is and take the derivatives and stuff comes out. Okay, and then is some answer that the answer is, I believe this answer checks out. So I won't say too much about that. And let's look at problem 7. Now problem 7, we have not that long of a function, right? It looks pretty innocent. But when you look at it more carefully, you realize that the derivatives is taking the derivative will definitely build your character, which I have no intention of doing. So I plugged it into the derivative calculator. Okay, and then found the various derivatives, and the rest of the stuff I just copy and pasted it, right? I mean, that is, I copy and pasted the first derivative and plugged it in to have the calculator crank me out the second derivative, and so on. And then I also have the evaluation calculator to figure out what the value at 0 is. So I figured out that the first derivative is, it didn't really say. Well, whatever. I think we don't care because we're trying to prove something about inflection point, maybe? What is the answer to this thing anyway? I don't even care about that. I just want to show you the derivatives, okay? And so once you got that, then you can get the answer. The point is I plugged everything in, and then the answer just came out very nicely, and I didn't have to do this. Now the book, of course, being written in 1947, all the students back then had to pull all the stuff out the hard way. Yeah, and which makes me feel thankful and happy that I wasn't born in 1947. Okay, so that is that, except that the graph here, this particular graph, I plotted it out, and I find it interesting enough to show you. Okay, it's not relevant to what we're doing right now, but it's just kind of neat, and therefore it doesn't hurt to take a look at it. Now, for example, here's some function, right, which is x times 1 minus e to the power x, etc. And if you are to plot it out, then it looks something like this. Okay, and let me move it a little bit so you can see. Well, whatever. It looks something like this, and it has various minimums and maximums. The purple line is, I drew the purple line to get, which is the same function without the sine x in there, because the sine x is spinning this thing up and down. So I want to see what the function looks like without sine of x. Then it looks like this upside down V-shaped thing, okay, which is okay. And so that is the function very closed in at about between, what is this, from maybe 5 to negative 10, that sort of thing. Now, if you zoom out a little bit to see what this function actually looks like, the function in reality on a somewhat bigger scale looks like this. Okay, and you see this is with the sign inside. Now with the sign, you notice that the function on the negative side spin goes up and down, and it also got bigger and bigger because the one without the sign, it goes down more negative, and the sign spins it up and down, right? So that it reasonably look like that. Now look at the positive side. What is that? That is, why would a function look like this? That, you see, this side is identical to this side. The only difference is that this purple line is diving down much faster. In fact, it's diving down so fast that we can't even see the angle here. That is, you need to pretend that this function is the same as this one. It has an angle, you know, where the things spread out, except that the angle is so close to 180 degrees that you can't tell. That's all, which is why the function looks solid. And this is still a function, even no matter how solid it looks. Okay, it just goes crazy basically because the angle on this side. Okay, instead of this is what 45 degrees, I think. You know, nice, so you can see it nicely. But imagine the angle spreads very close to 180 degrees, and in fact, I believe it's getting bigger. As this purple line dives down here, it will go more steeper and steeper as it goes down. So its slope increases as much as it is. Its slope is constantly increasing. It is going to infinity. So then, so as far as we can plot it and be able to see it and understand it with human vision, this is what we see. Okay, a giant mess. But I thought that was kind of neat that this function would do that. It's not relevant to what we're studying right now, and I don't know that it will ever be useful or anything, but I just thought it's something neat to mention. So next, let's look at problem 10. And somebody's swimming or running around some circular pool, okay? And you are supposed to figure that out. Now, we did this exact problem in Calculus 1. All right, so then eventually the point of the problem is that if you can either, here's my little graph, okay, here's my circular pool. I only drew half of it. But the point is, you can read us, here the lifeguard is on one end, okay, the drowning guy is on the other end. It doesn't say drowning here, but that's what it said in Calculus 1. So the lifeguard can get over there, either swim across, right, or run around it across, or do some kind of a mix, you know, that is you swim some distance and then run the rest, that sort of thing. So which one will be the fastest? That's what we're calculating. And eventually then you set up the problem. Remember the angle here, right here, being that it's a triangle on the diameter, has 90 degrees. But other than that, you just do, I don't know, basic trigonometry, and you end up with the formula of, where's my formula? That's F prime. Where's F? Swim plus walk total time, right here. I think this was X. Oh, X just the speed, so X means nothing. But anyway, so you eventually end up with this formula, and then you take the derivative or something. But you notice the derivative, the graph of this formula, is a graph that gives you the maximum. In other words, if you do take the derivative and find where it goes to 0, that will give you the slowest amount of time it takes to get from one point to the other. If the lifeguard hates the guy on the other side, want to get there as slowly as possible. Anyway, but that wouldn't make sense, really. I mean, why would a lifeguard do that, right? I mean, he wants the guy to drown, he can just sit and not do anything. Anyway, so here's the graph, and here are the answers. Yeah, and that's all I want to say about that. Now, so let's look at problem 11, which is a very similar problem, but 11 has a very interesting point. The author of this book actually gave a name to the guy that is doing whatever he's doing in our math problem. And I just want to mention that Weary Willie is some kind of famous character back in 1947 when this book was written, okay? And how do I know that? It's because I Googled it, because I was puzzled as to why did the author specifically mention a name, okay? So, but anyways, this is, again, some kind of a Calculus 1 problem. And so I did it here, okay? Please look at that yourself. What happened is the train, we are assuming that the train started when Willie woke up, the train, the front of the train is already right across from him. That's the assumption, okay? And then, so when he start running, then he has to run towards the train, and then eventually the train will be over here. So then, I mean, this from circle to circle is the length of the train, and the assumption is that Willie is going to reach the end of the train and jump on it while the train is going at 20 miles an hour. Of course, needless to say, I highly recommend that nobody ever even think about doing such an odd thing. But my answer, which is also the answer of the book, is that Willie has to run a minimum speed of 12 miles an hour, which is a very fast run. Okay, I think that's probably what most people, the fastest anybody. I mean, most average people can run is 12 miles an hour. My treadmill only goes up to 10. So yeah. Anyway, so that is extremely fast. And then there's some angle, yeah. So that's all I did. Okay. So if you have you can look at this, but it's fun to just do this yourself one time. All right. And that should be the end of this section.